So first of all, welcome to our session on monitoring and benchmarking of geospatial workflows, also Earth observation. In the original title, it was focusing on Earth observation, but I think we can generalize. Most probably, you are also working on different geospatial workflows, and benchmarking and monitoring techniques works equally for them as well. And today, in the second part of the session, we will introduce you a tool which you can use for benchmarking and monitoring purposes, and you can use it for Earth observation plus for geospatial generic computing purposes as well. My name is Serkan Girgin. I'm an associate professor at Faculty of Geoinformation Science and Earth Observation, shortly known as ITC, of the University of Twente. I'm also head of the Center of Expertise in Big Geodata Science. So our center is specialized in big data and cloud computing technologies and use them effectively and efficiently for research purposes, but at the same time for capacity development and education. So we are performing research on those topics, and we are also supporting the departments and our colleagues in our faculty. So as part of our work, we are also developing tooling. The tooling sometimes focus on improving the performance of geospatial computing workflows. Sometimes it's about publishing geospatial research data. This is also something we do most of the time, and there are some best practices we can follow for that purpose, and we develop some tooling. And specific to this session, our focus is in fact about monitoring and benchmarking workflows to improve their performance, resource utilization, and hopefully to make it reproducible. So that's basically okay, let's start. So we have around, I think, 80 minutes. So today's session has mainly two parts. So in the first part, I will talk a bit about why monitoring is important and why benchmarking is important, and what are the best practices to perform monitoring and benchmarking. We will have some interactive sessions. I will ask some questions to you, and actually we will review also a paper very quickly. And then in the second part, I will show you a tool that we developed, which we call GeoBench, which enables you to perform these monitoring and benchmarking tasks easily. I will explain the key features of that tool, and then I will make a demonstration about how it works. We will show you two cases. One will be a very generic Python-based case, and the second one will be also an interactive notebook, which performs a basic Earth observation analysis, and we will monitor how it works. Okay, so the geospatial data is getting a bit bigger and more difficult to analyze. So because we have now a lot of data sources that are available, so satellites, drones, etc. And in the previous presentations today and yesterday, I think we heard people processing terabytes of data, even petabyte level. That is really quite big. But it's not only the volume of the data, but sometimes the data is also complex, like SAR, INSAR computations are quite advanced. And most of the people nowadays are also interested in deep learning, machine learning. So these are really compute-intensive tasks, right? So that means most of the time, these computations takes a lot of time. They are really time-consuming, and practically some of them are not possible to do by using your laptops. So you need something else to perform the computations. So there are some solutions available. So if your study area is relatively local or regional, and the data size is relatively medium, then you can use parallel computing capabilities that are available on your workstations, or even sometimes on your laptops, because all of our modern laptops have multiple processing cores that are available, and if you can use them effectively, you can do the computing in parallel, which will reduce the time. For machine learning and AI applications, unfortunately, the number of cores that are available are not sufficient. We need much more, and that comes from dedicated specialized computing units, most of the time GPUs. We have also TPUs, which are developed for that purpose, which have thousands of computing cores instead of 8 or 16 that we have typically on our laptops. So that really speeds up the computation significantly. But there's a cost that is involved with it. And what is the cost? If you use a GPU? energy. They are extremely energy intensive, so we utilize a lot of energy for that purpose. If it comes to the national, if your country is quite big, or sometimes we are interested in a continental or even global. So, and actually today in the keynote, we saw global examples, right? So that's possible. Then you need a distributed computing infrastructure, either by using a computing cluster on-premise or by using a cloud-based resources for that purpose. But whichever method you use, you need to have a sufficient know-how about how the systems works, and you need to have access to the infrastructure. Infrastructure is really a little bit complicated, even if you use your own laptop, honestly speaking, because we have a kind of hardware level, and in hardware level, there is a lot of complexity. In a distributed environment, the data needs to be transferred between the computing nodes, so the speed of the network becomes important, the storage speed, the storage mechanism becomes important, and the hardware that we use for computation, we have a lot of options that are available. So, and partly, in order to make the computations efficiently, you should actually have a understanding about how these things works, and you should know the strong points and the weaknesses of the hardware level, which is actually quite normally for nerds type of information. But then we have the software stack, and honestly speaking, the software stack is much more complicated. So even for basic computations, we have some low-level libraries which does this matrix arithmetics and similar operations as fast as possible. On top of them, we have some high-level libraries, which, for example, in case of Python, most famous is NumPy, which enables us to use these low-level libraries in an easy way. We have Dask, which enables distributed computing. And on top of it, we have the machine learning frameworks, high-level machine learning frameworks, some compilers for that purpose. And in fact, your code is here somewhere at the highest level. And most of the time, you only know your code, and you don't know how the rest is taking place. So this also becomes a kind of complication, because it is like driving a car, but not knowing how it works, right? Sometimes it's not a problem, because most of the time we also don't know exactly how our car is operating, but still we have a understanding at the basic level how it works. When we come to distributed part, it becomes much more complicated, and actually file systems, the databases, how the data is stored is also quite complex. And in order to make the computations efficiently, we need to know actually how these things works. So it is important because the same computing tasks can be performed by using different software tools. So this is especially the case in certain languages like Python, where we have a kind of inflation of packages. So there are many packages which are developed for the same purpose. The core functionalities are most of the time the same. We are using them either because they are popular, or we are using them because, I don't know, we started using it and we are just continuing, and we don't think to change them because we don't see any reason. But maybe they are really outdated and they are extremely slow compared to other options. So that really happens. And in fact, there are many software components which are not able to utilize available modern computing infrastructure, and even the most basic ones. So there are many packages which only use a single core of your laptop, even if you have many. And many packages, they are not capable of using the GPU, also for computing purposes. So overall, we can say most of the scientific packages are unfortunately quite outdated, honestly speaking. And computing without efficient use of resources is suboptimal and costly. And the direct cost to us is most of the time, the time itself. I think most of you are early career researchers or PhD candidates, master students. So you are spending your time, and most of the time you are waiting for nothing. It's, in fact, unfortunately, a fact. And sometimes even you cannot be able to perform the necessary computation. So in order to understand the situation, the first step is to monitor resource utilization. That's the only way to understand what is taking place. This is relatively easy to do. So because all modern operating systems, they provide some tools for resource monitoring. If you are using a graphical user interface-based operating system like Windows, macOS, or some Linux distributions, we have, in case of Windows, we have the task manager, which provides you actually a nice summary information about what's going on. On Linux, we have different system monitors, and in macOS, the activity monitor is available. For all operating systems, there are also terminal versions of these packages or tools that are available, which you can use to monitor and moreover record what is going on. This is especially useful on a cloud infrastructure where you may not have access to a graphical user interface. So that's why it is really useful to know how these tools work and be able to understand what type of information that they provide. And most of the time, the metrics that are available can be grouped as the CPU utilization, memory utilization, the disk I/O, so the operations that are taking place, network I/O, the data that you transfer. And in certain cases, you can also get information about the GPUs or energy consumption that's available. So I think most of you are familiar with this type of tools. So that's why I won't go into detail and I won't show you how to access that information. But let's try to understand what type of information it provides. Okay. So normally, these graphical tools, they have different components. You can see the CPU utilization, you can see the memory, disk utilization, and it provides also a kind of summary. It can provide the CPU utilization for the system overall, or it can give the CPU utilization for each core individually. So here we have 8 cores that are available, and the graph shows actually the CPU utilization, which is 0 to 100. And there is a computation taking place. So what do you think about this computation? Yes.
Paralyzed?
Sorry?
It looks paralyzed?
It looked paralyzed. Why you are thinking like that? Yeah, on all cores, there is sometimes some kind of activity that's taking place. Yes. Any other idea? Do you think it's an efficient computation? Huh? It doesn't seem, yeah.
There's a lot of unused resources on the core.
Exactly. So there's a lot of unused CPU capacity. So the CPU utilization is less than 10% in all cases. And in fact, this picture is not different if you open this task manager when your laptop is idle. So basically, this computation is not using any resources at all. It's highly inefficient. Here, we basically see the background activity that's taking place. So if you have such a picture, then that means you will be waiting a lot of time for the computation to finish, if your computation is not a very simple short one. And even for that one, probably you are waiting for 100 times more than it is feasible. What do you think about this? Again, we have 8 cores. Yes?
It looks like one of the cores is doing all the work.
Yes. So we have one core, which is 100% in use. And we have the rest of the cores that is doing something. And if you look at the timing, it's when it's not doing the computation. So in this case, this is an indication that the software that you use is optimized for a single core computation. It is pushing one core to the limit, but because it is not a parallel or multi-threaded application, it cannot use the remaining cores. So this, in the modern computing environment, is considered also inefficient software. It's highly inefficient because even if you use a state-of-the-art server with 100 cores, it will use only one core. Okay. What about this one? Things are started to change a little bit, right? So sometimes it is a little bit complicated. I will just give you one hint. So in this case, actually, the CPU utilization is around 100, so only one core effectively in use, because all these peaks are at different places. So at a given time, there is only one core that is around 100%. So the computation is jumping from one core to another. So this results in a kind of inefficiency. Sometimes the systems are doing this automatically to reduce the temperature, for example, and not enforce one core. But sometimes this is due to the programming the library or basically the algorithm. So, but this is, although it looks like it is doing some computation, all the computation can be boiled down to a single core. So that's why this is also a highly inefficient computation. If you have a picture like this, then that means the situation is getting better. So here we have 1, 2, 3, 4 cores, almost 100% actively in use, and the other cores are also doing some computation. So this is a kind of picture where we have multi-threaded computation that is taking place. Having multi-threaded computation is relatively easy if your algorithm is suitable for that purpose. Pushing multi-threaded computing to the 100% limit is tough. That requires optimization. Sometimes it may not be possible in certain languages, for example, if you use Python. Because Python has some overload coming from the interpreter. Sometimes it goes to the interpreter, it doesn't go to the computation. So that's why you cannot enforce 100% utilization all the time. But if you have a picture like this, then that means you are really using the resources at a good level. If this level comes to the top, then you are really using everything like this. Here we have a very specific situation. As you can see here, we have a very high number of cores that are available. I think we have 24 cores, right? Half of them are fully in use, and half of them cannot do anything. Any idea why it may happen? This is a little bit scratch technical, huh? Not enough to do, or?
Waiting for RU?
Yeah.
Or use 12 cores instead of 24, maybe you specify it.
One reason could be this. So maybe the software while running is set to run only half of the cores. That might be the reason.
Maybe our data is chunked that you only have 12 chunks that it can operate on.
Number of chunks is not always equal to number of active cores. So the chunks, because I mean, the chunks you can send to different cores. So it might be possible that you have.
If I have 12 chunks, I cannot send 12 chunks to cores on third.
Yeah, that might be the case. Yeah, that might be the case. That's true. But this is actually a specific case when you have hyper-threading. So on Intel architecture, each computing core, actually we have a physical computing core, and then we have 2 threads connected to each computing core. They share the same some computing components, infrastructure, and because they share, if one part is actively in use, the other one cannot do the computation. So that's why actually these two cores are connected to each other, and because one is doing something that blocks the other, it cannot perform the computation. That's basically the reason why it looks like so. But overall, this is a nice, good picture. Okay. So given that, let's assume that you are operating you are an infrastructure operator, and a PhD candidate came to you and told that he or she has an advanced machine learning workflow, which processes a large number of Sentinel-2 scenes, and the analysis is taking too much time, and asks you to give more accounts so that the computation, she or he can use these multiple accounts to do the computation in parallel. So we check the CPU utilization, and this is what we see. So what shall we do? Shall we give the account? No, we shouldn't, because eventually the computation is taking place only at one core. There are many cores available. On a data center level server, we have hundreds of cores that are available, and that workflow is using none of them. And just asking for additional accounts will not help with this. So actually, it's better for that person to improve the workflow or use proper, more modern libraries which can do the computation in a more efficient way. So that's why, in this case, it's better to say no, unless it's very close to defense or whatever, right? Okay. So this is a story actually normally on your laptop, but the story is not very much different if you move to the distributed computing or cloud computing, because those systems are not magical tools. So it's not like if you move your computation to a computing cluster, it will speed up, or everything will start working in parallel. This doesn't take place. So you really need to prepare your workflow and the code so that you can benefit from the infrastructure. The recent libraries, the frameworks, they really lower the barrier a lot. They are relatively really easy to do, but still it requires significant time and effort to understand and get competent about how to use it. So that's why it's very important to read the documentation and learn how it works. And scaling blindly, so just assuming that when you run your code on an HPC system, it will run fast. It is not correct, and it is most of the time suboptimal and costly. And don't expect people to warn you also. That's the case. Okay. So now, our interactive part. So we have, I have one question to you, and that is, how often do you check resource utilization while running your computing tasks? So you can go to Vulk Lab and enter OGHSS or scan code.
What's the code number?
Sorry?
What's the code?
Code OGHSS, like OpenGeoHub Summer School. Okay, it looks like we have two winners. One is rarely, and the other one is often. That's good. So we have people who are really checking from time to time, and we have people who are not checking. So that means I think this session will be helpful for everyone, which is good. Also, we have never and always. That's also nice. Okay, good. Especially never is good. So if you don't know it, you don't care about it. As long as you get the result, it doesn't matter, right? Okay, good. Thanks. So, but in order to make informed decisions about suitable computing strategy for yourself, you should also not only monitor, but you should also benchmark. So if you sometimes when you search on the internet, for example, I have this code, I want to speed it up. So or, how can I do that? Most of the time, people tell you, okay, test it, right? Write the code, test it. That's the only way to understand. And that's actually quite true, because most of the time the code that you have is quite specific, and it's very difficult to say if you do that, it will speed up. So that's very difficult. So that's why you need to really test. So, and when you come to testing and comparing the things, you enter into the benchmarking. And benchmarking is the systematic process of measuring and comparing performance of a system or a method against a standard reference point, which we call the benchmark, or against the peers. So you may have two codes, you can compare them to each other, or you may have a kind of standard and you can do the comparison for that standard. So in both cases, we have a benchmark. So benchmarking actually might be critical component for your work, even if you don't think it is the case. So let's of course we can classify the research activity into different groups, but for a very basic division, you might be working on the application of an existing methodology from your domain to a specific study area or domain. So there's already something which people implemented. You have a different study area, you implement it there and try to address it, right? So these applications we call application studies. So probably some of you are doing that. Then we have application of an existing methodology from another domain, and you just transfer it to your domain and try it. This is called methodological transfer. Another option is to improve an existing methodology. So there is already something, and we try to improve it for better accuracy or for better performance, right? So this is most of the time what we do. This is a methodological improvement. Or you can develop a new methodology completely to address an emerging issue, maybe. Or you can develop a new methodology with a better accuracy or performance compared to existing ones. So it's innovative. So it's a state, you are advancing state of the art, okay? If you do methodological improvement, or if you do a state of advancement, benchmarking is the core of your study, because you need to show that your method is better than others, right? But if you develop a new methodology, or if you apply an existing methodology from another domain to your own domain, this is still important because you need to show that the methodology is feasible. If you come up with an idea which requires 2 years of computation to come up with a result, it's very difficult to convince people to use it. So that's why you should run it. You should show that it is fast, it is accurate, it works. So that's why you also need to provide some information about the benchmarking. And even for existing methodology, it is the same. So basically, there is almost no escape from monitoring, measuring, and reporting that information in your work. Okay. So then my next question, what is your research contribution topology? Let me switch. So are you working on like application study or methodological transfer? You can pick multiple, that's possible if you are doing multiple of them, but just to know.
Do you mean the second one by domain as in research area?
Research area, yes. For example, we can take something from medical field and transfer it to Earth observation.
Yeah.
Okay, I think we here also we have a kind of clear winner, which is methodological improvement. So it looks like most of the people are really trying to improve something. That means you really need to know how to benchmark and how to monitor the process. Good. Okay. So unfortunately, that's a little bit tricky. So that's a little bit tricky because when we need to report this monitoring or benchmarking, we really need to be reliable. And ideally nowadays, we need to be also reproducible. So in the actually in the previous talks, like talks of Edzar and the talk before, so there is a lot of mention about reproducibility issue, right? And in order to make this happen, there are multiple points where we should be careful at. So, and which can be divided into 5 categories: experimental design, workflow documentation, data management, performance metrics, reporting, and transparency. Okay. And for all these points, there are some best practices that we should follow. So for the experimental design, it's very important to standardize the hardware settings. So even on your laptop, you have power mode. You can set the power mode to balance mode. You can set the power mode to the maximum performance, right? And depending that setting, you will end up with different results in terms of timing. So that's why you need to standardize. You need to sterilize the software environment. So the laptop that you use is a lot of software, and there are lots of background processes that are running, which may affect the computation. So you need to minimize those processes. If you do some randomization, you need to fix the seeds, and you also need to clear all the caches that are available, because when you write a file to your hard drive, most of the time it's not written to your hard drive, but it just stays in the memory, and it's done at a later stage. And it looks like it is a very fast operation, but in fact, it is not a completed operation. It's just a lazy operation. So you really need to minimize. That's why you need a controlled environment for that purpose. You need to use equivalent parameters across tools if you compare different. So if you compare QGIS, for example, against ArcGIS, for example, for a buffer operation, you need to make sure that they are using the same number of points by creating the buffers, which is actually impossible, because ArcGIS doesn't allow you to set the number of points that you have. And if you do a blind comparison, you will see that QGIS is much, much faster than ArcGIS. But the main reason is because it's putting less number of points compared to ArcGIS. So it's virtual, so it's not real comparison. But people do that comparison, and they tell that QGIS is faster, which is not true. And you should run also the workflows multiple times to account the variability between these different runs. That is, we call repeatability. So these are all design-related things. When we come to the workflow management, so it's very important to describe each processing step, parameters, and configuration, so that people can repeat it. And from people, I mean you as well. So after 1 year, 2 years, if you want to repeat it, you should be able to do it, and that's the only way. If you don't do the documentation properly, there is no way. You can provide the scripts and notebooks in a version controlled repository, so make them available to others. You can list the library versions, the software environments, and more importantly, also the hardware configuration that you use for benchmarking, so that people can understand what type of environment is in use. And if you want to also follow the best practices, you can combine most of this under containers. So you can use Docker or Singularity, and provide container images so that people can run your code in a more reliable manner. When we come to data management, unfortunately, that's the biggest difficulty that we have especially in Earth observation, because the data sets are very big. Most of the time, we are getting data from large repositories, and those large repositories are not reliable. So you can download 100 scenes one day, and 1 month after, maybe you will get 101, or maybe you will get 99. And sometimes they tell you they reprocess the data, so you can even not get the same data, but you will get completely new versions. So, and that's very difficult. So that's why, if it is possible, you should always create the copies of those files and make them publicly available, if possible. If not, you should really provide a very good documentation about the data with the complete metadata, so that people can have a look and understand. And you should also fix the versions of the data sets as much as possible. There are some nice recent developments. So now we have some data repositories like Git, which works similar to Git, which enables you to have versioning of Earth observation data. So maybe you can consider using them. For the performance metrics, it is very important to record wall clock time. So what we mean with the wall clock time is the time that you see the computation is taking place. For example, if it is 5 minutes, that means you waited for 5 minutes. But if during this 5 minutes, 100 cores are in operation, in fact, you did a 500 minutes of computation. So this is a CPU time, which is different. That's why it is important to record also CPU and GPU utilization, track memory consumption, disk I/O, network, and energy consumption. Especially energy consumption is becoming much, much important nowadays, because in our domain, we are trying to solve most of the time issues that are related to environmental quality. And while doing that, actually, it's possible that we are damaging the environment. So that's why it's a little bit responsibility. So we need to be responsible while using those resources. The performance should be always measured with different data sets and with different complexity data. And it is also very important to check not only the timing, but also the correctness and the consistency of the results. So sometimes it looks like you get the results, but the results are not correct. And if you don't do the test, then basically your benchmarking is also not correct. Finally, the reporting and transparency is also very important. So you should record the inputs, intermediate outputs, and the logs for full traceability. So just providing the output is most of the time not sufficient. You should always provide the log files and intermediate files if possible. Providing plots, easy to understand visuals is also very important. This enables people to better understand the results. And it is also very important to indicate the assumptions that you have and potential sources of bias and the scenarios where results may not generalize. So sometimes you do computations which are extremely specific. So there are limitations, and you should indicate the limitations while providing this benchmarking results. So if the process that you use can only work on polygons, but if it doesn't work on polylines, you should indicate this, because the alternative option might be doing both of them. Okay? And it is really important to publish these metrics together with the workflows and data sets so that they can be repeated or extended by other people. Most of the time, we publish our workflows because we create a source code, we create a notebook, whatever, and we publish it, right? We publish the data sets that we generate most of the time at the end of the activity, but we never publish this kind of performance metrics. So that's why it's really important to publish this information and make it available. So these are the best practices that needs to be followed. Any questions about best practices?
How much sense does it make to run these experiments on different hardwares? Because do we need to make sure that we really test our workflow and not the underlying infrastructure?
If your intention is to test the infrastructure, then you should test it with different infrastructure.
No, I don't want to test the infrastructure. I just want to make sure that I'm not accidentally testing the infrastructure instead of my own workflow.
Well, there is no escape from it, actually, basically, because you use an infrastructure, and basically some performance parameters are linked to the infrastructure that you use. So that's why if your intention is to test different methods, then using a single infrastructure is okay, as long as you describe the infrastructure fully, so that people can understand the differences. Okay. Otherwise, there is no need.
Okay.
Yes.
Are those more general recommendations, or is there some sort of standard that we should report these and these?
These are partly recommendations. From my point of view, these are the minimum things that you need to do. But as you know, this minimum is a quite long list. So, and unfortunately, as researchers, this long list is really increasing a lot. So it's the same with the research data publishing, for example. They ask to provide a lot of metadata. At one point, you need to draw a line. If you are really publishing a continental or maybe global data set, I think you should follow everything. If you are really publishing a small data sets, maybe you can scale it down. Okay, it's a little bit up to you. Any other questions? Okay, then I have a short assignment to you before we move to the second part. So let's analyze the benchmarking paper. So you can find this. This I selected randomly, so there is no. The intention is not to criticize this publication. I just saw it and I said, okay, maybe we can use it for this purpose. So it's about comparing the performance of 3 different GPUs to perform ResNet 50 training. So you can download the article by following the link or the QR code. So I give you 5 minutes to have a look at the paper and try to identify which best practices are applied and which are missing. And what's your thinking about the paper from that point of, I mean, not scientifically, but from this completeness point of view? Okay. Okay. What do you think about this paper? Good practices. Any good practices? Yes.
They mentioned that they containerize.
They containerize, yes, they mention it. Do we have any kind of access to that container or any information regarding to that container?
Not sure.
Yeah. That's what they say, actually. They say they are container, but there is no proof that they did it, unfortunately.
But have a repository before.
Yeah, there is.
They mentioned also all the content there.
Ah, okay, that's good. Okay, that's good.
Even look it up.
Okay, that's nice. Any other good practice?
They state their limitations.
Sorry?
They state their limitations.
They stated limitations. Okay. It's good. Do we have access to a benchmarking data? Is it available? Doesn't seem to be, right? So the details of the computation is also not available. They say they are basically comparing these three different GPUs, one Apple M3 Pro with 36 gigabyte of memory. This is a significant amount of memory, right? And then RTX with 6 gigabytes only, and then Tesla T4, which is 16 gigabytes only. So basically, actually, the type of things that they compare are a little bit significantly different from each other, honestly speaking. So in terms of computing capabilities and the memory, which is actually a kind of limiting. And they didn't try to limit it, but just let the system use the memory if it is possible. So that has a kind of direct impact on the results.
Because in the end, the focus is mostly on the speed, right?
This is what they do. Actually, they say, okay, we have these resources and we just do the computation on the resources and we look the output. But this kind of computation is unfortunately a little bit unfair because eventually speed is only one parameter that you have. Another one is cost. So if you need to pay for the services, most of the time, the ones with the limited resources are cheaper than the other ones. So then you need to do a kind of optimization there. And here we don't have any information. Partly because they are using also a cloud-based system because this Tesla T4 is in fact on Colab. And on Colab, you don't have physical access to T4s. You have actually shared access to T4s. And basically, there is no information about the operating system there also. And for all of them also, we don't know it. So for Apple, we only know that it's a macOS. For the other one, we don't know what is the operating system. No information about the working environment. They only named certain packages, and they say the software stack was identical. So we need to go and check their source code if they really fix the versions, and if they fix the versions, that might be the case. But among different operating systems, that is really sometimes a significant problem. So it's not so easy to have the same versions. And the same version of the package doesn't guarantee that you have the same version low-level libraries linked to that. They are different. macOS doesn't use actually the standard BLAS or similar matrix accelerator libraries. They have their own implementations. So the underlying infrastructure is in fact different. It is really a little bit difficult to say that this benchmarking is, first of all, reproducible easily, and the reliability is also a little bit questionable because not all components are well described, and access to data is also quite limited. So, but it is a kind of standard benchmarking that you can find. It's very difficult to find benchmarking papers or papers where this kind of performance is indicated, most of the time the information is extremely limited. That's why it's not reliable. When somebody tells, that's why I gave the example, QGIS is faster than ArcGIS, you should always question. It may not be the case, and that's also the same with this. And this is a quite recent publication, so basically, so that's really a kind of state of the art. But this, we can improve. We can improve the situation, and in order to improve it, actually, we have a tool that's available. So now that's the second part. So we developed actually a Python package with a command line tool to monitor and benchmark geospatial workflows, which we called a GeoBench. Actually, we see that it's not a good choice because in the morning also there was a mention of another GeoBench. So probably the name will change, but just for the time being, you can access through these links. We have also an online documentation that's available. You can check. So what GeoBench is doing is basically it has some key features that facilitates geospatial benchmarking. So it has a robust benchmarking framework implemented, which tries to ensure as much as possible a controlled environment and at least report the environment properly so that people can understand. Then it monitors all critical metrics with minimum overload on the system because you are performing the computation and at the same time you are trying to monitor the computation. So this monitoring action should be really quite light so that it doesn't affect the computation itself. This is what we try to make happen. We support multiple executors that are common to geospatial workflows. So you can use it, for example, to run a Python workflow, a QGIS workflow. So these are supported. You can define scenarios, and those scenarios can automatically generate different sets of parameters. So you can easily test different options automatically. We are providing machine and human-friendly benchmarking outputs and reports. And it also it provides automated storage of input and output data. So for each run, you have also a copy of what the input data is and what the output that is coming from, so that you can compare and make sure that the outputs are as expected. So for the time being, so it's in alpha phase. We just published today. So our intention is to just make it ready for this session, in fact. So we are supporting shell commands. So it's possible to run Windows or Linux shell commands. You can run Python scripts. For QGIS, we are supporting QGIS processes. So or QGIS Python scripts. So if you have something you can test. And we are also supporting Jupyter Notebook. So if you have a Jupyter Notebook, you can also run it through the system. What we collect. So the system does a baseline monitoring and end-line monitoring, which means monitoring before the testing starts and after the testing. And in that case, we are collecting metrics at the system level. So we are measuring everything that is taking place. And we are also measuring all the processes that are running at that time. That means that all idle background or active tasks that are running are recorded. During the monitoring, we monitor all the processes that belong to your workflow. So your workflow could be multi-threaded, multi-process. So there might be hundreds of processes that are taking place. We are monitoring all of them for you at a very high resolution. But at the same time, we are also measuring system level metrics so that you can follow what other things are taking place, if they are taking place. So what is the idle situation? And we are also recording all the processes that are running, but at a less frequency, because normally there are thousands of processes that are running, and collecting that information is really time consuming. So we minimize this operation during the actual monitoring phase. Some additional metrics will be available soon, like we will support GPU usage, process level network I/O, and energy consumption. Energy consumption is available for Mac for the time being. For the others, we are about to support. What you get. So basically, once you finish, you end up with a directory structure where you have the results as a machine-readable JSON file, which includes all the details. We have a HTML file, a single HTML file, which you can share. It doesn't have any other dependency, which provides complete results in a nice visual way. And then for each set that is created from the scenario, we have a folder. So let's assume that you are running a script and there is a buffer parameter. You say the first value is 100, the second value is 200. Set 1 is the output for 100, set 2 is the output for 200. So, and for each, you have the summary of all the runs that are there, and you can indicate for each set how many repetitions needs to take place. So in this example, we have 4. So that means you have buffer with 100 4 times, buffer with 200 4 times, and each result coming from that run is stored as a JSON file. All the input files are stored, and the output file is also stored. So this is basically what you get. You can package it and you can upload to repository to give a benchmarking result. Or you can just publish the HTML file so that people can see. How to install it? It's easy. So for the time being, it is not in the Python package index, but it will be there soon once we solve this name conflict. For the time being, you can install pip, by saying pip install git plus GitHub ITC grep geobench. I already shared the presentation. It's on Matterdown, so you can just click and do that. Once you install, the system automatically installs a command line interface. By saying geobench and the name of the scenario file, you can run your scenario automatically. It is also possible to modify some parameters of a run. So normally the scenario includes the number of repetitions, but you can change it if you want by providing the parameter, or you can also set the output directory to store your output results in a different place. Defining scenarios is quite easy. So you just create a YAML files. In the YAML files, only 3 parameters are mandatory. You indicate the name of the scenario, the type of the scenario, and the command that you want to run. In case of Python, it's the name of the Python script. In case of QGIS process, it's the name of the QGIS process, like your native buffer. You can indicate how many times you want to repeat the test. If that script or the process accepts some arguments, you can indicate the values of the arguments. If they are individual values, they are taken as they are. If it's a list of values, then for each value, a new set is created. So in this case, we have the distance parameter. It has 2 options. So that means for this test, there will be 2 sets. In this example, we have 2 arguments, and for each of them, there are 2 parameters. That means there will be 4 different sets, each running 5 times. So we will have 20 runs that are automatically done by the system. Okay. You can indicate the inputs and outputs. If they are indicated with the named parameters, then they are also provided as input arguments. And then the system automatically stores the input file and the output file. And because it recognizes the geospatial files, it doesn't only save the shapefile, but everything that is linked to that as well. That's the intention. So it's not fully implemented yet, but it will be the case. It's also possible to use it programmatically. So you can use it, for example, in your Python code or in Python notebooks. How to use it? So you import the geobench class and create a geobench instance by indicating parameters like the output directory, the number of monitoring run, the duration. You start the monitoring by providing a label, do your work, and then stop it. Here it looks a little bit complicated. The reason is normally you can say start, do my work, and stop. But if your work creates an exception, then it will exit and then you will lose your recording. In order to prevent this, we put it in a try block so that the exception is erased. But in any case, the finally block is run by Python. So the monitoring is stopped and the report is generated. So even your code fails, you have all the recording until the failure point. Okay. A simplified version of this, if you have a single method, then you can use a decorator. So we have a geobench This one is with the capital start, the other one is with lowercase. You can decorate your function, you can set the same parameters, and once you run it, the system automatically handles this for you. And a report is automatically generated and saved. Okay. So this is how it works. And this is how it runs. So now this is a little bit complicated. I will try to explain you in a few minutes. Please bear with me as much as possible. So what we do, we read this YAML file, we look all these different options, we generate the scenario sets, we create the executor depending on the type and store that information. Then we perform a system cleanup. So we clean all the caches, make it ready. Then we put an idle wait. So we wait for a certain time, like a few seconds, just to stabilize the system. And then store the system information. So what is the status of the CPUs? What's the memory? What's the frequency that they are running? What's the operating system? So that kind of information is stored at this point. Then we start a baseline monitoring. So for 5 seconds or 10 seconds, we record the system as it is. And during that period, we understand if there are significant background activity that is taking place. So this enables us to understand. Then we start the sets. For each set, we load the arguments that are set for that set. And then for that set, we start the runs. So for example, the buffer is 100. So our argument is 100. And the repetition is 4 times. So that means we have 4 runs with 100. So that's the idea. At the beginning of each run, we do the system cleaning again, because we do the run. After the next run, if you don't clean the things, they might be in the cache. So we do the cleanup, we wait idle, we perform this baseline. So before each run, we also record the system activity, do the task, record the monitoring, wait a little bit after this operation, and record the end line so that we measure if there is something, some activity is ongoing afterwards. That's normally not expected, but sometimes things are delayed. So this enables us to understand if there is a delayed execution that is taking place. And then we store information. We store the end-line information. We store the input and output data. We don't store, for example, large files while the computation is taking place, not to push the system that is taking place afterwards. We take all the runs. We calculate the average statistics for each run. We store them. And at the end of all the sets, we also do a final end-line monitoring of the complete system to see if everything is stable or not. Okay, this is how it works. It's a little bit complicated, but actually the idea is basic. So make sure that everything is clean, store the previous situation, record, store what is taking place afterwards. Now, let's show how it works. Demonstration. Any questions at this point?
If you run the benchmark,
Yes.
do you get an estimate of how long it will take?
No, that's not possible. Yeah.
For me,
That's very-
the most frustrating part, that I run something and I don't know
Yeah.
how long it takes or how long it will wait. So it's 5 days I need to wait or
Yeah.
5 minutes. So that's
Yeah. That's another thing that we are working on. So basically, actually, Edzar didn't explain much, but there's something called OpenGeoHub, which is a kind of Google Earth engine, but open source. That has the capacity to have the estimate. It can tell you how much resources it will take, also approximate the time. Yeah. Yeah. With arbitrary Python code, it's impossible. That's why I can tell you. So in order to make this happen, you need to have a framework and
Always find the question.
yeah. So, sorry, that's the problem, unfortunately. Yeah, that's not possible. Okay, so let me show you now. You can also try it at the same time if you wish. Make it a bit larger. Is it visible? Shall I make it bigger? Okay, this should be, I think, better now, right? Okay, I will create a empty directory. And then I will do the git clone. ITC grep geobench. Sorry. Okay. Actually, we can. Okay, let me do another way. So first, I will create a virtual environment. That might be better, right? Yes, this might be better. So either you can git clone, and after git clone, you can install from the local copy, or you can create a virtual environment, or if you want, you can also use your active environment. You can activate, and then you can make pip install, and in that case, you can use this git plus HTTPS version. And this will basically retrieve the code from the GitHub repository and install the dependencies and make it ready for your use. We have really a minimal set of dependencies, so just basic packages, nothing else. Most probably for actual computation purposes, you may need to install some additional packages. Okay. So meanwhile, for the demonstration, we created a very small package. So if you go https://data.script.u20.nl/geobench/demo.zip. So this address, you will download a small zip archive. And in the archive, we have some files. These are the files that we need to use. Mattermost, okay, Aditi will do it. Yeah, I don't have it's open, but okay, Aditi will do it. Yeah, this is the data. Let me copy this.
Could you show me the link once again?
Sure. Okay. So now, if you enter GeoBench, the command line will work, and it will tell you that argument missing, which is the file name. So we need to provide the name of the scenario. So we created some example scenarios. The most basic one. So the ones with the YAML extension are these scenarios. The most basic one is this count primes Python simple.yaml. So as I mentioned, there are only three things that are mandatory: the name of the scenario, the type of the scenario, and the command, which is count primes.py. Actually, this count primes.py is also a Python code, and by default, it takes half of your course, and it tries to check the numbers, prime numbers, up to a limit, which is in this case 1 million. It is possible to have some parameters. One parameter is the course, so you can say, okay, instead of by the default half, just use 4 cores, and in this case, it will only use 4 cores in parallel to calculate up to 1 million. And by using the number parameter, you can change that 1 million. Okay, that's the idea. So if you use GeoBench with this basic one, So the system will read the scenario. It will calculate how many runs will take place. In this case, we don't have any arguments, so there's only one scenario with one repeat and one run. It creates a Python executor. It sets up the output directory by using the name of the scenario. And it stores the executor configuration inside. Then it clears the system cache and waits for 5 seconds before the run, all the scenario run starts. It stores the system information, and it does a baseline monitoring for 5 seconds. It executes the run, scenario set1, run 1. And actually, here you can see the output using 8 cores, checking numbers up to 1 million. And this part is coming from the script. So this is the output of the script. And then it waits until the run is completed, does an end-line monitoring, and completes the benchmarking. Okay. So once this is done, what you get is a folder. And inside the folder, you have first this results.json file. And this result.json file includes all the information about the test. So the system, the CPUs, the utilization before the test, the memory, the disk storage, baseline monitoring for 5 seconds, and each 1 second measurement took place, the start time and end time of baseline, all the processes that were running during that baseline. And once you skip this, basically you come to the actual computation. In the actual computation, you can see all the process IDs that are part of that computation, how much CPU was in use, how much bytes are read, and the memory that is utilized by the system. So this is for machines, basically. Then we have the human-friendly version, which is a report.html. And this report.html provides you a nicer view. So the system information, hardware information, the executable that is used. Then we have the information about the set. So there's only one run. It's 100% successful because it went well. It took 7 seconds to finish. And because it's only one, we don't have any standard deviation of execution. Then we can see the average CPU utilization, the average memory, average process memory, CPU percentage that is in use. You can see the baseline average and the end line average. As you can see, the baseline before the computation takes place is quite low. So that means the situation is good. And afterwards, we have a little bit higher, slightly higher, which is normal because the system is just finishing the activities. Then you can see the system-wide CPU utilization. So in our system, we have 16 cores. You can see this how this 16 cores were in use. And you can see actual process utilization while the test was taking place. So we asked the system to use 8 cores. That's why we have 8 cores in parallel. We have 8 different processes, and each process is using almost 100% of CPU. So we should see that it is quite good. You can also the memory utilization. You can see the I/O. So because everything is taking place, we don't have any I/O operation. So that's why it's empty. You can see the timeline. So this is about 6-7 seconds, and the first is always 0 because it's the reference. But then we have a quite high CPU utilization. You can monitor memory utilization, and you can see also the name of the processes and how many threads are in use and what's the CPU utilization. So there are 8 Python executables that are doing the computation. There is one Python executable which is doing the monitoring, and one Python executable which starts this 8 processes. So everything is visible from there. Okay. So this is the most basic option that you have. There is another one. So it's the same thing, but in this case, we are telling to the system to use two values for cores, which are 4 and 8, and two numbers also. So it creates the combinations, and from these combinations, it will create 4 different sets. So if you run this one, the system will warn us, indicating that the output directory exists and it's not empty, and it aborts. Because the name is identical, the output generated is identical, you can enforce by entering the clean parameter. And if you do that, then the system automatically cleans the output folder and starts doing the benchmarking. And this one now is really doing the benchmarking. So there are 4 scenarios, 2 repeats each. So there will be 8 runs in total. That's why it will take a little bit more time. But because we have multiple runs for each set, we will start to get the standard deviation. We will start to see what's the difference between each run. And it will be possible for us to see also what's the time it takes with 4 cores, what's the time it takes with 8 cores, what's the time it takes to reach 1 million numbers and 2 million numbers. Is it linear or is it really going exponential? So it provides you information about the workflow that you have and the scalability at the same time. Any questions? You can do it through the shell functionality. It's possible. You can do it. Yes. Yeah, R needs to be installed, and then you need to indicate the path of the R, and then it will work. It should work also with Julia. Yeah.
Validation kind of things that's different, or typically they do it manually and then have a parameter or something that's for the number of folds, or how should you do that?
What do you mean with that? It's not very clear to me.
So if you do cross validation, so you want to run the same benchmark multiple times and on different training and test data sets, that's an application I use a lot, but maybe it's less frequent to your spatial data. And then what I was thinking, how would I set up my parameters such that it's just for each a run for each of the folds of my cross.
Actually, it may speed up at least the process. Like you can have a ratio parameter, and in the ratio parameter you can indicate different options, and the system will automatically say, okay, 10%, 90%, 20%, 80%, 30, 70. It will create everything automatically for you, and then if you compare the results, you will see how things change.
That's exactly it.
Yeah, that's possible. And another thing you can do, you can have a set, a single set, like 30%, 70%, but then you can have a parameter for randomization, and then you can create different sets of 30, 70, and you can see how it works. That's also possible. Yeah. So this will continue a little bit, and meanwhile, let me, range of input files. Yes, that's possible. Yes, it is supported. It's supported. So yeah, it does that for you. That's also quite good, because in that case you can really process different sets of Earth observation data or different sets of vector data. That's also possible. Anything that is list becomes actually a new set. That's basically the idea. Let me show you very quickly how to use it in Jupyter Notebooks, and then we can finalize. This will continue. It will not have the actual results, but it's okay. Okay.
And also install the requirements to the XT.
Sorry?
Requirements to the XT. There is the requirements.
Yeah, I will do it. I will do it. Okay, now I'm just installing Jupyter Lab just to show you the Jupyter instance. Aditya, actually, by the way, Aditya is also one of the developers of GeoBench. So we are developing together with Aditya because he's on the other side of the table. He's there, but normally if I think we don't have much time available. So the system also supports QGIS, and he would normally show you how it works with QGIS, but I think this we will skip for the time being. So we just created a very basic notebook to calculate NDVI. In the zip archive, you will see a NDVI calculation.py, which includes basically utility functions that are used. The notebook is here, and there is a requirements.txt, which installs the packages that are required for this NDVI calculation. And actually, these are basically the usual suspects. So we have like the Daska, ODC stack, PyStack clients just to get the data. GeoBench is also indicated, so it installs it again. It should be okay. Meanwhile, actually, what you can do, I will just move on to the next question. What other features would be nice to have? So if you think some features would be nice, so you can type them. We will be very happy. Or the ones that you like, you can also indicate. That's also okay. It's possible to give some thumbs up also if you like it. Okay, this is done. So I start Jupyter. Okay, this is the notebook. So it has some information about what it does. But basically, actually, it uses stack to define a temporal and spatial extent, and filtering on cloud percentage. It uses ODC stack to load the raster. Performs a cloud masking by checking the SCL band and stores the output as a geotiff. So this is what it does. It's very basic. So for that purpose, basically we have this utility functions. The code is there, so you can have a look what they do. The way to let me do it, make it a bit larger. So you just import from GeoBench the GeoBench class, and then you create a GeoBench instance. The instance has the parameters that are identical in the scenario file. So in the documentation, we have a complete documentation where you can find this information. Then we are defining the time range and also the bounding box. This is actually Wageningen area here for 1 month in 2023. So do the monitoring. You just start, indicate the name, do your work, whatever you do, and then stop it. That's it. So let's run. So now the system automatically, I mean, all this, when you run it on command line, all the information that is provided, now provided as output. So you can see what it is doing. So it did the end-line monitoring, and actually now it is finished. And so the result if you look at the result is a Python dictionary. It has all the information, but at the same time, the system automatically creates the folder like a command line and can put the results also there. Because we are in the Jupyter environment, you can now more easily have a look at the content, browse it easily, or you can actually create the report as an HTML file. And if you do that, then a HTML file will pop up here. And it has some JavaScript in it, so that's why it's better to open it in a new browser tab. So just right-click, open new browser tab, and then you access the report directly. And you can see the total time, you can see the network utilization. In this case, actually, the system downloaded something. That's why we have the network activity. You can see how much data is transferred, which is very good because we talked about cloud-native data formats. We talked about ZAR. We talked about cloud-optimized geotips in the morning, right? But they are sometimes on the theory, so you should really test to see how much data you transfer, actually. And this is a way to do it. So you can really run your code and you can compare ZAR versus cloud-optimized geotiff to see what is the performance and how much data you transfer. So the good thing is, just let me finish with that one. This report can be extended. So the first part was only for looking data. Now we are starting a new section. We called it load dataset. And in this case, we are loading the dataset. So if you run this, the system will start a new processing. Under the root output folder, it will create a new folder for that section. And under that section, it will put the benchmarking information. And it will also automatically update the summary component. And if you save at the end the report, like we did here, then the HTML file gets also updated automatically. So once this is finished, so right now, we have only one set. So here we have search catalog, and there is nothing under that. So it's only the output that's coming from there. Once this is finished, we will have a new section, which is called load dataset, and we will see the performance of that part. This will take some time because it's now downloading the data. We just published the tool today, so that means it may have a lot of issues. So we will be very happy if you can have a look and open some issues on GitHub or a feature request. We will be very happy if you can also contribute. So if you have some ideas about how to improve or some additional geocomputing that we can support, that would be great. By the way, the computation is now finished. So if you actually go there and just refresh the page, you will see that now there is a new set 2. And in that set, basically, we have information about data downloading, which took about 70 seconds. And you can see the baseline activity, the actual activity. Now many cores are taking place. And actually, we also downloaded some files. In reporting, I think we have some issues. It's definitely not 25,000 megabytes. We didn't download that many. So that is something we need to check, but at least we have some information about the data content. Okay. So this is how it works. There's also timeline. Okay, down there. Yeah, you can also hear. That's interesting. You see, because it's I/O operation, so there is some CPU utilization very small, and it's waiting for the data to come, asking for data, retrieving the data, so you can see this content very easily, which is good. So this is how it works. We hope it will be useful for you. So, but independent of this, there are many other tools that are available which you can use for benchmarking, for monitoring purposes. I highly suggest you to do it regularly so that you make sure that you use the resources, because it will save your time. Everything will finish much more faster. And yeah, it will be also less costly for us and for environment. Okay. Thank you.